Can we just start over? Is that okay?
Yeah.
Okay, cool. So I'll record here for sure, and then we'll just start over.
I'm recording too, so you're fine.
Oh, you're recording as well. Okay,
Yeah.
awesome. So that's fine. Okay, so going back to our node traversal, Amini,
I'm here.
right? So we started at the root node. Currently, I'm at 1, correct?
Right.
Okay, so we said we visiting the left side of the tree recursively, correct?
Yes.
So that means keep going left until there's nothing else to go to.
Okay.
You with me?
Yeah, that I totally get. It's just how did we? I mean, I don't mind we go through it over. It's just the how do we how does it start back? Like where does it start back after 5?
Okay, let's go ahead and do it. So we go 1, 2, we get down to 4, correct?
Mm-hmm.
So at 4, we print what the node is.
Yeah.
There's nothing else to go to, so we print what that current node is at 4.
Okay.
You with me?
Yes.
Okay, so we have 4, and at that point we visit the node. The node that pointed to 4 is 2, correct?
Yeah.
So I print out 2, and at that point there's nothing else on the left. I printed out my current node, which is 2. Now I need to look at my right side.
Mm-hmm.
So the right side of 2 is currently at 5, correct?
Yeah.
So I print out 5. So far, so good?
Yeah.
And since it's recursive, remember, if it's recursive, there's still calls on the call stack. There's still calls on the tree, on the call stack, sorry. So now I need to backtrack and go return my calls to the function.
Okay.
Okay, because one is still not done yet.
Yeah.
I haven't printed out 1.
Okay.
How many?
Yeah, yeah, I'm following.
I haven't printed out 1, so currently I have to look at 1 and print out 1, right? Because it says visit node. So in that case, I have to print out 1, right?
Yeah.
I've seen the left side. What's remaining?
Okay, so I get it. So it's one currently is the node that we're looking at for 2.
Exactly.
And then it's gonna print out the light. Okay.
So currently, if I'm at 1, what's remaining to look at?
3. It's right.
3. So at that point, we are done traversing the tree. Questions? How many?
No.
Anybody else? Any questions? You want us to go over it again?
I have a question not to go over, but for example, if 3 node would had a child, like some number,
If
what would be next? Yeah.
If 3 node had, let's see, change this. If 3 node had a child here, like this, correct?
Yeah, so after 1, we would visit the 3rd child or 3 first?
After 1 would go left first, right? Would go left. Left would have to get printed out first. So if I had a value here, say 10.
Yeah.
10 would get printed before 3.
Before 3, so it would be 1, 10, 3, and the last to the right. What we?
Exactly.
No. Oh yeah.
And then if I had like 9 here, 9 would get printed. Right, so it would be 10, 3, and 9.
10, 3, 9. Okay, okay. Thank you.
Awesome. Let's erase this and keep going. Any other questions before we actually jump into code? Yes, Chelsea, you're on mute. Go ahead.
Yeah. So if they were back, it would be 1, 2, 4, 5.
If they were, say that again.
Because I get that it goes left first, but once it gets to the middle, I kind of get confused. So it's,
the middle here. Sorry.
Yeah, like basically anything that's not the left. Like
the middle here.
No, lower down.
Here.
What am I looking at?
What middle? Like what? Give me the value. What value?
Like
between, like when you have 9 and 10 on the 3.
Yeah, yeah, yeah.
So you okay with 4, you okay with 2 and 5?
Yeah.
You're talking about 1.
No, but like if the other branches were back, like the 10 and 9 that you had, that's where I get confused because then I don't understand where 5 would go.
This way?
Yeah.
Okay, so we still printing the left sides first,
Yeah.
right? And then we'd print out 1, right? The same order we have here. Would print out 1 currently, correct? Would go down to the left side. So if I had 9 here, I'll print out 9 before 3.
9 before 3.
Because
so,
remember, if I'm here, I need to go left first.
So you go 5, 9, then 3, 10?
Yes.
In that bubble. Okay.
Because I cannot print out 3 before I get to 9. Cool?
Okay.
All right.
So like Alex, the way I usually imagine in order traversal is like if you drop down all the nodes to like a surface level, they would like appear in the same order that you would see as the tree. So it'd be like 4, 2, 5, 1, 9, 3, 10.
You're talking about like this here, right? So 1, 2, 3, 4, 5. So you'd have 4, 2, 5, 1, 3, correct?
Yes.
And it becomes almost like a link list.
Yeah, exactly.
Okay.
Like, because if you think about in order traversal is just going everything from, you're just reading everything from left to right, essentially. So just like bring it down to like the ground and read it from there.
Everybody?
Does that make sense? I know it sounds a little weird.
Nah.
That actually helps a lot.
Yeah, that's great.
That makes a lot of sense.
What the hell was that? Sorry. Oh
That's
my
just
god.
some static. That's just some static coming in there.
Okay, I thought there was a robot.
Almost. Okay.
What did he say to do it to make it simpler?
Basically saying like drop in those values down like this. And then it becomes 4, 2, 5, 1, 3. It becomes this here. So you see the tree, you just collapse the tree.
Okay.
I'm sorry?
Okay.
Cool? Tiffany? All right, awesome. Yeah, feel free to jump in as you guys need, or whatever that helps the classroom visualize better. Thank you, sir. Okay. Any other questions before we continue? Any other questions? Awesome. Okay, so let us continue on here. So we'll create a new playground. We'll call it BinaryTree, and we'll just hyphenate it with depth first traversal. So let's go ahead and create a new playground. BinaryTree. Ooh. Happy fingers. BinaryTree, try that again. Depth first traversal. Okay. BinaryTree is what we're doing. And today we're talking about depth first traversals.
Can you make it bigger, please?
Yes, definitely. And we said depth order traversals. We have 3 types.
Antonio, I think I need to be let into the. I'm trying to log in from my phone.
Antonio?
You got it.
I got it. Thank you.
So we have in order with the first. We have pre-order. And we have post order. This is the tree we'll be using. Oh, if you're not currently speaking, please probably mute. Our root is 1. And we have 1, 2, 3, 4, 5. Okay, so we'll do a little bit of review. Basically, we'll construct a tree here. So implement a binary tree node.
Hi, is this the very top where it starts at depth first traversals? Okay.
Yeah. Okay. So let's go implement the binary tree node. We'll start off with the class we did on Monday. We'll say binary tree node. It's a generic type. We said, what do we need? What's the properties of a binary tree node?
A value.
Set a value of type T.
A left child.
Left child.
And a right child.
And a right child. And we need an initializer to initialize our value. Cell value equal to value. And at that point, our value has initial value from the initializer itself. Great. Okay, we'll write an extension to implement our traversal methods on binary tree node. The first one we will be doing is in order traversal. In order traversal. And what's the rules here? We said visit left child recursively. Visit current node and visit right child recursively. Great. We'll write a function here. We'll call it in order traversal. Very similar to what we did on Monday. We'll use a closure to capture the value of the current node. So we write a closure here that will capture our binary node. So we could use a print statement later when we call our in order traversal when we're testing it out. So we'll visit binary tree node, doesn't return anything. And we're using recursion, right? So basically the steps we write here is basically those 3 steps we're doing in our actual function body.
Can we
So
just scroll up a little bit?
Scroll up. Oh, to the actual class?
Just make sure that's I wasn't missing anything. Okay, cool.
Okay, I'll just pause for a second.
And we don't have to initialize left or right child because they're classes, and we made them optional. That's the initializer on it.
Yeah, exactly. Because optional has a value of what?
Nil.
Yeah, of nil. But this one doesn't have any value whatsoever. So we have to definitely use an initializer for the value, but the left and right child has default values of nil.
Oh, wow. Alex, I just want to clarify that parents should have left child first. There's no situation that parents has only right child, correct?
You could have a right child only, and you could have no children. You could have a left, you could have a right, you could have both. Remember, a binary tree, the definition of a binary tree is, whoa, my kids are breaking the house. At most can
Have two.
2 children.
Yeah, but so in our example, if 3 had only right child, so our order would be 1, 3, and next child, correct?
If 3 had a left child, you said?
A right child.
If it had a right child?
Yeah.
Okay, so if it had a right child, the current node 3 will get printed before the left child.
Before the right child. Okay.
Yeah.
Thank you.
Good.
Okay. Oh, so we're doing the in order first?
Yeah, we're doing the in order first. Cool. Okay, so we in a binary tree node, we have access to the left child here. So remember we said left first. So left is happening recursively, correct?
Mm-hmm.
All right, so on left child, we'll call in order traversal, and we'll pass in visit closure.
And that recursively just meaning over and over again.
Until it's no more.
Right.
Exactly. And then we visit the current node, which is self in that case. And then we go ahead and we call the right child recursively. So right child in order, and we pass in visit here.
Okay, hold on.
One benefit of recursive is as you say it is what you write. So exactly what we said there, we visit the left child recursively. This is what we're doing. We say left child, go ahead and keep calling in order recursively until there's no more left childs to call, right? If left child is nil, it's not going to call anything else. It's done at this point, right? And as it goes, it's going to print out what the current node is. And then go to visit the right child recursively as well. So the order 1, 2, and 3. So in all 3 traversals, the only thing we're doing is changing what the orders of those things are, right? But the order always, the left is always before the right. Regardless of any of the 3, left is always before right, okay?
Maybe I'm doing some.
You have an error?
I don't have an error, but at first it was saying that the visit was void as if I couldn't use it, but then I still could. So
you're not calling visit, you're just passing visit. So you're not saying
I know,
visit.
but when I put the visit there at first, like when I took it out to type in visit, it had a line going through it.
Oh, that's fine. You can just ignore that.
Yeah, the same thing. Just type it in anyway.
Thank you, guys.
Thanks, Ahad.
And Christian.
And Christian.
My people. We appreciate y'all. All right, all good.
How we doing? Good? Okay, let's test it out. Test in order.
So it's recursive because we're using the function inside
itself. So left child, which is a node itself, it calls in order traversal, passing itself. So itself checks to see if there's more on the left side.
And it'll keep on doing that, and then it'll print self before it goes over to the right side.
Exactly. So this is self here. It calls itself and calls itself until there's no more left sides. And then it prints itself. Self is 2. Cool. Test in order. Let's see what we're gonna do here. Did we create a tree yet? No, we have not. Okay. So I guess we should create a tree.
Oh, but we don't have it to print. So should we have a?
We're gonna print it in the closure like we did on Monday.
Okay.
But first we need to create a tree because we have no tree. Create a tree. We could just copy, but we're not gonna copy anything. Let's just say tree node here. Tree node is a binary node and it's of type integer. You guys will get a chance to create a tree that's a string later for like practice. But now we're just using a tree, which is integers. And my value is 1. And we have 5 nodes. Second value is 2. Third value is 3. Fourth value is 4. And fifth value is 5. So we have 2. We have 3. 4, and we have 5. And let's go ahead and connect them. So we'll say tree node dot left child equal to 2 node tree node dot right child equal to 3 node 2 node dot left child is what? What's 2 node left child? 2 node left child is 4, correct?
Sorry, I couldn't keep up fast enough.
Yeah, I was still typing.
Oh, with the actual constants here?
Yeah, I'm trying to practice my speeding instead of some people.
So 2 left is 4, and 2 right is 5.
Yes, so
2 right is 5.
tree node dot left child is equal to 2 node. And then so tree node dot right child is equal to 3 node.
So we're starting with 4 node, right?
Is that? Christian, what's that?
We're starting with 4 node?
We started, you mean the very top of the tree, the root?
Well, I mean like the traversal order if we were to start.
Oh, you mean like when you actually print it out?
Yeah.
Yeah, the first one should be 4.
Okay.
When we print it out. So here, expected output, I guess we could put expected output. When we drew what we did, we said it was 4, 2, 5, 1, and 3, correct? Correct?
Mm-hmm. Mm-hmm. We said it would be, yeah.
Yeah, that's what we drew out on our whiteboards, papers. Somebody's multitasking. Are you doing laundry and coding at the same time? Chelsea?
Oh. I can't see.
Are you doing laundry and coding at the same time? How are we doing? Can we write the test or call the closure? Yes?
Yep.
Okay. So let's go ahead and say tree node dot in order traversal, and we just have a node argument because our closure expects an argument node. We have a node argument here, and now we could simply go ahead and just say print node dot value, and we could use our terminator like we did. Terminator.
That's what I was going to ask. So the tree node knows all the rest of the information about its two nodes.
Because we capture it in the visit closure.
No, I'm saying that the tree node itself knows that the two node has a left child and that the two node has
exactly.
The top knows. Okay.
Yeah, because that's how we connected them.
Okay.
Yeah. That's how we connected them. Without connecting them, there's no relationship.
Okay.
So we're using the pointers here. Those are basically pointers. So I'm saying my first tree node, go ahead, the left child, or basically the left child pointer is the two node. Right? So that's what I'm doing. I'm constructing our actual tree as we did. Cool?
I'm thinking.
Questions before we continue? Madame.
So, Alex.
Yes, sir.
So, in order traversal, like
1, 2, 5, 1, 3.
what you wrote in the extension was like a visit closure, right?
This guy?
Yeah, and that was recursive.
Yes.
And in the function that we write outside of it, we're just saying what we want to do with the visit
node,
closure.
yes. Well, yeah.
Visit closure, sorry.
Yeah,
Oh,
exactly. Because we could do more things there. We could put in an array. We could check to see if it's positive, whatever we need to do.
Okay, cool.
But our basic objective is just to print out as we have them.
But the way it would usually go, right, is like first, like, you know, we go through the first tree node, which is 1. And then we call the left child, which is going to be like 2.
Mm-hmm.
And then when we get to 4, if there's no more left childs, we use the visit closure on 4.
To capture that, yes.
So like
so
we
in that
print
case,
4.
4 is self.
Yep. And then we're going to go back to 2.
It backtracks.
And then print 2. And
yep.
Because we've done visit on self already, we're going to call the right child traversal right after that. And we're printing 5.
Exactly.
All right. Good to know. Thanks.
Yep. So backtracking is the big terminology there, if you have to use that. Ahad?
Yeah, good to know.
All right, cool. Okay, so everybody implemented their tree node dot traversal, the function, call the function with a trailing closure.
Yep.
Okay, and in our trailing closure, this node is coming from our function definition. Our function definition has a closure here, which has one argument of a tree node. So that's what we actually use again in the actual call function. And it captures the nodes along the way. So now we're able to print them and see what order they are. Are they the correct order in the order we expect? Okay? Hello?
Yes.
Okay. I'll just put a print statement here to basically break our terminator for the next part of this exercise. And we'll put a print statement here to say what we're doing. So in order traversal. And let's go ahead and print it out. Let's see what we have. Oh, did I run that already? Okay. Is it automatic? Wait, no, it's not. Okay, so we have 42513, right? That's what we initially drew out on our whiteboards. So that's the output we expected. That's the output we got. Did everybody get that same output? Can I get thumbs up for outputs?
I got the same output.
Okay.
I'm actually missing the 3 at the end. Can you scroll up? Maybe I missed something.
The connection, maybe. Did you set up your nodes correctly here? 3 node.
I didn't. I did not. I said okay. Found it.
All right.
How if we had if you added what was the output if you had the 9 and the 10 ones still, or the extra 2 digits that you had?
We need to connect them, right? So let's go ahead and connect them. So you're saying you want some more on left and right here?
That's right.
Okay. We could use any values. Let's just keep them consistent. 1, 2, 3, 4, 5, 6, 7. What's about that? 1, 2, 3, 4, 5, 6, 7. So we need some more connections. We need to connect 6 and 7 to 3. All right. So let's connect some more nodes here. 6 and 7. And here we have 6 and we have 7. Cool. And 3 node left child is 6, right? Eric, you with me?
Want to be here?
Eric?
Yeah, that's how I have it.
Then you have 3 node dot right child is 7, correct?
That's correct.
Okay, so we connected them. Let's go ahead and print it out.
So you made me turn off my fan to leave?
Madame, mute. Okay, so here we have 6 and 7 getting printed first. Well, not 6 and 7. What do we have here? We have 4 to 5. That's what we have here. Let's go ahead and draw it out. We have 1, 2, 3, 4, 5, and we have 6, and we have.
Alex,
yeah.
I was only 4251.
I'm sorry?
I was only getting 4251. I think I messed up somewhere in the in-order traversal.
Okay, 1 second. Eric, I'll come back to you, okay?
Okay.
Okay, so let me just comment that out. And run that again. So you're not getting 42513 as we have here currently, Christian?
No, I'm not. I'm only getting 4251.
4251. So is your 3 node, let's see. Are you connecting your right child to 3 here?
Yeah.
Right child to 3, right?
Mm-hmm.
And in your in-order traversal, do you have as what we have here?
Wait, I think I found it. Hold on. Oh, yeah. I messed up. Instead of a tree node, I wrote 3 node.
That's okay. No worries. Any other questions before we continue?
That was it. I'm sorry.
No questions.
Okay, let's go back. And so Eric wants to see what happens when we have more children here. All right, so let's just run this. And let's go to the drawing. So this is the expectation, right, Eric? That's what you got?
That is.
You said yes, correct?
It is.
Okay, so let's just go back to the drawing and see what's going on. Is everybody with me? Everybody still have their scrap paper or whatever they're using?
Yep.
Okay, so let's go through that again. Okay, so we agreed that, we agreed that we're looking at the left side, correct? Awesome. And then at that point, we have 4, right? 4 is that node we capture, visit self. That's the current node. So far, so good?
Mm-hmm.
And what does enodor say? Enodor says left, print out the current node, which is 2, and then go right, correct?
Mhm.
All right, so at that point we have 5. And what do I do from here? Right now I'm in the left branch. Can we see my dotted line here?
Mm-hmm.
Okay, what's the next node we're looking at?
1.
1. Okay, what's the next thing we're doing?
We're going all the way down to the 6.
We're going all the way down the left, right? So all the way down left here. And what are we printing?
6.
6. And what's the next thing we do?
Go back up to the 3.
Go back to the 3. And what was the next thing?
Print out the right child.
Print out the right child. 7. Come on. 7. Cool. Good. All right. So going back here, this is what we have. 6, 3, 7. Good. Eric, does that help you?
It does.
All right. Cool. Any other questions?
Thank you.
Any other questions? Questions?
Oh, you said that if we don't put the print new line, it's not about this. Sorry, if we don't put the
this guy.
new line,
Oh, yeah, this guy
yeah, if we don't do that, then whatever else that we write after would just be
on the same line. Like if I do pursuit here, and I don't do this, and I print out. Pursuit is going to be in the same line.
Oh, wow. Okay. Thank you.
But hey, if I want to break it up, I just put like a print statement here, break that up. Make sense?
And that just like shuts that off.
Yeah, I think an empty print statement should work as well because it does have the new line as well. Let's just verify here. Right? Yeah, it depends because the new line gave us an extra line again between them. Remember?
Yeah.
But the empty string or whatever, empty print statement just gives us a new line.
Yeah, perfect. Thank you.
Awesome.
I'm glad Eric asked that because
no, it's good. It's good. It's
Todd's
good.
idea of just like collapsing it for the in order also makes it
helpful.
Very.
Very, very good. All right. Let's take a short break, like 5 minutes, and then just come back. So you guys could just like stop your video or whatever, and then come back in 5 minutes. So it's 11:03. You could come back at 11:10. So keep your video or whatever, just like, or just stop the video or whatever, and mute as well. Cool?
Yeah.
Good?
Copy.
All right, awesome.
You're muted, by the way.
Alex, you're muted.
Do you think if we say it loud enough, he'll hear us?
He's never gonna hear you.
Oh, damn, that sucks.
Everybody back? We have 29 minus, right? So we should be good. Okay. All right. So we have 2 left. So far, what have we done? We've done in-order traversal. We'll diagram out pre-order traversal and post-order traversal, and we'll just come back and code what it looks like. Because so far we've seen the only difference when we come back and code the 2 different traversals is which order we have the traversals be in, right? In order, left, the current node, and right, right? So left node, right, right? Pre-order, you do the visit cell first, and then you do left and right. And post order, you do the visit self last. So that's the only differences between the 3 of them. And as I said before, left child is always before right child, right? So if you're at some interview and you're like, oh, you know, just think pre-order, you print out the node first, you print out the node first, post, the node is printed last, right? Like the root of that branch there is printed last.
I'm still unclear on, like, the question itself. Would they ask you about binary trees, or is it like they're going to ask a question and we're going to have to decipher whether or not we're dealing with a binary tree? Because I'm not entirely sure where this applies.
Yep, they could ask you a question like, given a tree, find the height of a tree. That's one question that could be a valid question. They could give you a question like, given a tree, go ahead and print out in such order, in some given order, right? Like you'll be given a tree. There's a lot of different tree questions, right? Like common ancestor, there's a lot of different trees.
So you'll know when they're asking.
Yeah, they'll give you, exactly. Okay. You'll know if it's a tree question, like just based on the prompt, right? Unlike a dictionary or an array question where right away, you know, maybe I use a dictionary to go ahead and track some given numbers, some given values, but most likely you'll know if it's a tree question.
Okay, thank you.
Right? But when you get deeper into like data structures, like graphs and stuff like that, then as far as like what traversal, what tree it is, that kind of thing, it's different.
Sorry.
Cool.
Yeah.
Good. Okay, so let's keep going. Actually, let's go to our whiteboards. Let's go to our whiteboards. What do we have? To just reiterate, we did in-order traversal, and we'll do now pre-order traversal. So pre-order. But just to take one step aside here, Chelsea, I shared a document with us yesterday or the day before, just diagramming what, where is it? So when you talk about questions about like what's pre-order or what question could relate to it, if you're trying to example, again, later in the course or when you get to your interview, there's different uses for like pre-order, in order, there's always different uses for it. One of the reasons, or you would probably want to use a post order, for example, here is to delete a tree here, for example, right? Post order traversal is used to delete a tree. That's just one of the examples of what order you would use, because it goes from the bottom of the tree up to the top.
Okay, yeah, no, that makes sense.
Exactly. So just glance over that document as to the different use cases for the different traversals we've done or we'll be doing today.
Okay.
Awesome. We all have that document, right? It's also in Canvas. I added it to Canvas on the DSA review. Thank you. So back to our pre-order traversal here. Let's draw out our tree. And we'll just go with Eric's tree right away to have more children. So we'll have a full tree here. And there's a lot of trees, like concepts we haven't covered yet. We'll come back to again. There's balance trees, there's complete trees, full trees, AVL trees, all sorts of trees. we're just going through basic traversals of trees. How do I go through a tree? Because a tree itself is not straightforward like an array, for example. I can just say for, X going to my collection, right? I have to figure out what traversal I want to do. Cool. So what do we have? We have 1 at the top, 2, we had 3, correct? And we had 4, and Eric, 1, 2, 3, 4, 5. We had 6 and 7, right, Eric?
Yeah.
All right, thanks. So here we want to do pre-order now. So pre-order basically is you want to do visit the node first. Then you want to go left. Again, left is always before right. And then, so left recursively, and then right. Okay. As we go down left recursively, we also print out the current node. That's the one difference. So the way we go about it, we print as we go. So we'll see 1, we'll print out 1, we'll go down the left branch recursively, and as we come across those nodes, we print out the values right away. Because in the recursive call, remember you call in yourself. So if you call yourself again, you're printing out your value of yourself. So what does that look like? First we have 1. Let me actually just go down the tree. Actually, I'll just write it out and stop me if we have any questions. So I'm going down the left branch, but first, before I go down the left branch, I want to print out what my current value is. Tiffany? I want to print out what my current value is. What's my current value? I'm at the root. What's my current value? 1. Okay. So I'm going down the left. And again, as I'm going down the left side, I'm printing out the values here, because every time I'm calling recursively, I'm printing out myself. So 1 followed by 2. What's the next value?
4.
4. All right. Awesome. What's the next step?
You would have to go back to 2, but would you print 2 again?
I've printed 2 already, so it's not on the stack anymore.
So then 5.
So based on, yeah, exactly. So based on our rule here, we want to print out 5. Okay. So far, so good? All right. What's the next step? So we visited all those nodes here. I'll just put a dot here.
You go to 3.
I go to 3.
Print out 6. And then 7.
And then 7.
I don't get it. Why isn't it 6 then 3?
Why is not what?
Why isn't it 6 then 3?
Why isn't it 6 then 3? Because you're printing out self first. Like if you see here, you're printing out self first. So you visit the node first. Basically, the visit is the way you print out the nodes. So every time you call the function again, you want to print out the current value first. Remember, it's pre-order. So you want to print out the node first and then look at the children.
So the node is like the root of the branches?
Where you currently are.
Oh, okay. The children. Okay, got it. Yeah.
Awesome. Any other questions about pre-order? So this is pre-order traversal.
Well, this seems pretty straightforward.
Okay. So,
what use does pre-order have? Like, why would we use this?
Again, they all have the different use cases. As you go deeper into trees, there's different use cases for why you want to do pre-order versus post-order versus in order. The document I shared with us goes deeper into it as far as like where we'll be heading deeper into curriculum. But for now, we just want to know what it looks like to print something in order, pre-order, and post-order.
I do have a question.
Yes.
Are we, and it's a little, are we still in, we're no longer in unit 5, like after this project is finished, right?
I would say we're in CTA unit.
Okay, so CTA own unit.
Yes, CTA unit, basically iOS CTA, DSA CTA, and then after that we go into hackathon unit.
Oh, so unit 5 and the CTA wasn't like the final for unit 5?
Well, the final for unit 5 was basically CTA, correct? That was what we just completed, right? So that
Yeah.
was the CTA. So basically that's like they're about the same, like unit 5 CTA, right? But CTA, I would call it like its own unit,
Okay, cool.
right? Because we're going through like DSA stuff too. We'll revisit DSA more again later in the units, especially like as we go into capstone.
Okay.
We'll be doing DSAs in the morning, for example, or iOS topics in the morning, like iOS, like Swift 5.2, whatever that's new, Swift 5.2 we want to talk about. But more importantly, like there's other topics we have to cover, like core data and stuff like that.
Yeah.
Before we get into like what's new in 5.2. All right.
Just curious.
And that's like more like unit 7.
Okay.
Cool. Okay. Awesome. Any other questions? Trees. So, Christian.
Being Benito asked a question in the chat.
Okay, we need a chat manager. Let me jump and see what you might ask me. Telling me the question.
He said, "How does it know to go back from like 5 to 3?"
So it backtracks, right? So recursive. The way recursive. If we go back to the recursive lecture we did, I introduced the notion of a call stack, right? So if you have a function on the call stack, it needs to return that value to somebody, right? So as I call in things on the call stack recursively, they're on the stack, and as they get called back, they get backtracked. So as it gets backtracked, those values needs to be received somewhere. So it's the notion of a stack, right? We'll revisit recursion tomorrow again to see what that looks like on a call stack. But basically, if you're using recursion, you're using a stack, because every recursive call goes in the call stack, right? Like we introduced recursion with factorial, for example. So as we're making our factorial calls, they're going in the call stack until they get popped from the stack and there's no more calls on the call stack. So every call needs to return a value. So as we're going down the tree recursively here, let me go back to it. As we're going down the tree recursively, so I go down to 1, I print 1, I go down to 2, I print 2, I go down to 4, I print 4, right? But there's still 2 on the call stack. So 2 itself, 2 here, 2 is still on the call stack. 2 needs to visit its right child, right? It needs to visit its right child because that's still on the call stack. So tomorrow we'll take a look at what, again, we'll revisit recursion tomorrow with a simple example like using factorial and see what that looks like. Because if I'm doing a recursive call, every call goes on the call stack, right? So if I have, for example, I have some function here, call it recurse, and say we call it recurse. Say we call it recurse 4 times, for example.
Can you hear me?
Yeah, go ahead.
Oh, no, I'm just listening.
Okay, so say we call it recurse 4 times. If I say call it recurse 4 times, obviously we need to have a base case there, like how to stop it. But for example, that's just a pseudocode, right? So if I'm calling recurse 4 times, what happens? There's gonna be a call stack here. Every time I call a function, that function goes in the call stack. We spoke about that in the recursive lecture. But every time I call a function, it goes on the call stack. So the first time recurse gets called, it goes on the call stack, recurse. It gets called again, goes in the call stack, recurse. Gets called again, goes in the call stack, recurse. And gets called a final time, goes in the call stack, recurse. So at that point, for example, on our tree example, if this is 2, right, on the call stack, 2 at this point, it's still on the call stack. So it now needs to decide, have I seen my left child? If I haven't seen my left child, I need to go ahead and call it, right? Same as if I haven't seen my right child on the call stack, I need to call it. Because now I need to get myself off the call stack. Because remember, when you return a value to whoever called the function, it needs to pop out of the call stack. And eventually the call stack won't have any more calls. Does that help you?
Okay.
Right.
Yeah.
So just keep in mind.
So when it gets to 3.
Go ahead.
So when it gets to 3, basically 2 will get popped off and 1 will still be on the call stack, correct?
Exactly. Because it's not done.
Okay.
So anytime, like, basically recursion and stacks work together. They're cohesive. If you're doing recursive, you're using a stack.
Okay.
Okay, so that could almost
All right,
say
thank
like,
you.
hey, yeah, very welcome. That could almost say like what we did with breadth first search. What data structure did we use for breadth first search?
Then we use hold on. Well, basically a node,
But
right?
how did we print it? How did we print it? How did we keep track of the children we visited?
That we visited.
Yeah, on Monday when
Basically,
we created a different data
mm,
structure to keep track of the children.
oh, queue.
Yeah, so there you go. Perfect. So as we use the
Okay.
queue, keep that in mind, like write that down somewhere. Thank you, Ben Benito, for bringing that up, right? So we use the queue to traverse a tree using breadth first search, right? As you see it, you want to go ahead and print it out. So we use a FIFO data structure. So first in, first out, right? Now we're using the notion of what's known as backtracking. Now we're using the notion of what's known as backtracking. What does that mean? I need to visit other nodes later, so I put it on a stack, right? And we're using recursion here. Recursion behind the scenes, it's a stack, right? So basically depth first search and stacks or recursion works hand in hand. And a queue and a breadth first search also works hand in hand there, right? So what I would say breadth first search. Breadth first uses a stack, a queue. Uses a queue to keep track of visit nodes, right? That's what we did on Monday, right? And what we're doing today, we're saying depth first search or depth first traversal uses a stack. In our case, we're using recursion. Again, if you're calling something recursively, every recursive call goes on the stack, right? So implicitly, let me actually redo this. So here I'll say depth first search uses recursion, and I'll say implicitly uses a stack by nature of recursion, right?
So wait, every function technically is on the stack, correct?
Yes, yes,
When it's
and
called.
that's called the
Okay.
call stack, right? So very good.
Got
So every function call goes onto the call stack. Very, very good. So if it's still on the stack, you still have to work with it.
Okay.
Cool. Awesome. Thank you for that, sir. Okay, so good. That helps you, right, Ben Benito?
Yes.
Okay, thank you. And we hear your
Sorry.
voice. I think that's the first time we heard you on Zoom. So
Okay.
your thumbs up and applause is here for Mr. Ben Benito. Thank you, sir. All right, so we did pre-order, right? Let's go ahead and do post-order now. Any other questions before we continue? Any other questions? So let's go ahead and do post-order. So we have our same tree going. Numbers 1, 2, 3, 4, 5, 6, 7. And pre-order states that, anybody want to tell me what pre-order will do? I mean post-order, sorry. What does post-order do?
It starts at the bottom on the last.
In the 3-step process we have, like where does visit go? Where does left, right go? Basically our 3-step process here. So for pre-order, for example, we say visit node, we say left and right, right?
Left and then right with the view with visiting the node as the final process.
Okay, very good. So left and right. Chelsea, that's what you were saying, Chelsea?
Yes, but I started with right, forgetting that we always start with that.
Oh, okay. Got it. Awesome. Thank you. Thank you, Matt. Thank you, Chelsea. Okay. Awesome. So here we do not print the node as we go down the left side. Okay. Do we see where the left is? Left is, I mean, not left. Do we see where the visit node is? It's the last thing we do. Do we see that? Everybody, do we see that?
Yep.
Right. So in our rule block here, we say left child recursively, right child, then we go ahead and we print out the node that we're looking at. So what we want to do, we want to go down the left side. We go down the left side, we print out 4. What's after 4?
2.
5. I see a 5 in Chelsea's hand there. Okay.
I was on mute.
We don't do 2 because 2 at that point is the visit node part.
Oh, okay.
Right. Okay, so we do left, we do right. And then what else do we do?
Go up to 2.
Go up to 2. Thank you, May. That was May, right?
Mm-hmm. Yeah.
Okay, at this point, what do we do?
I feel like somebody.
Tiffany, was that?
No, I feel like somebody said to put 2, and you said no, we don't write 2 because that's visiting the node. But you meant that for 5?
Because here it says left first.
Right, and then right, and then
right, and then we visit 2.
Yeah.
Yeah.
Okay, it's okay.
No, I heard 2 before 5.
Okay, maybe that's why. That's why.
Yeah. Okay, cool. What's the next step?
Would be like 6.
It would be 6. Awesome. Very good. Everybody heard Yulia here?
Yeah.
Yep.
Right. So Yulia said 6. We're not looking at 1 because 1 is still the top node there. So 1 actually gets printed last. So very good. So Yulia says 6. And then somebody
7.
else?
7.
7. Very good. And then
3.
3.
And then
1.
1.
1. Awesome. So this is our post-order traversal here. And as we see, we do the bottom there, and then we go up to the top. Awesome. Okay. If we have no other questions, we'll go out and code the rest of it. And basically what we're doing in our code is just changing the order of our calls. So we have 2 other functions, just changing the order of them based on is it pre-order or is it post-order. And always remember, pre-order, you print in the node first, post-order, you print in that node last. Awesome. So let's go. We're back in our extension for binary node. And now I'm looking at in-order traversal. And now we want to go ahead and print pre-order traversal. It takes a closure. Again, we could have simply just printed out the value, but that's not enough. Because if you want to do any manipulation later, like the question gets more complex, you want to be able to have that node to deal with. Like if somebody tells you, go ahead and go through a tree and only give me back the odd numbers or the even numbers or whatever it is, you want to be able to capture that. So we're capturing it using a closure. Again, for review, a closure captures values. What does that mean? It captures, a closure captures values, stores values for use at call time. Cool. So we have pre-order traverse.
Can I ask, so when you actually have the 4.2, like how we had before, like the 4.2.5, that whole thing, when it's captured inside of the closure, is it considered an array that you can reiterate through?
You would have to store it in an array.
So
But,
you would
yeah,
have
like
to put an array inside of the function?
Inside of the trading closure. Like here, I could have an array to capture the values of my node.
Oh, so instead of printing it, you can just say for node, add it, like append it to an array.
Exactly.
Oh, okay, got you.
Because now we could do anything with that value.
Right. Okay.
But if it was a print statement, there's no way to capture that print statement. Does that make sense?
Right.
Because again, we don't say print in our database service. We have a closure, we capture it, and then we say, hey, go ahead and view controller, use the value as you need to. Awesome. So let's go ahead and do the visit part here. So visit is a closure, doesn't return anything, but has an argument here, which is a binary node tree.
So
and
inside of the closure, I'm sorry to cut you off.
No,
So
no. This is good.
Like let's say like right now it's not returning anything. We couldn't just have it to return an array of whatever we're putting into it.
Would have to capture an array here. Like if you want to capture an array of binary nodes, for example.
Okay.
But we don't have an array of binary nodes here.
Right. Okay.
Very good, very good. Awesome. So what's the order here? What am I doing?
We're doing
Tanya?
It would be visit self, right?
Okay, so Tanya says visit self first, right? Because at that point we want to go ahead and visit the node before we visit the children. Everybody with me? Everybody with me?
Mm-hmm.
All right, cool. 1 second. The kids, 1 second. Max, that is still teaching. Oh. Jeez. Sorry, he too is doing his schoolwork and his laptop is about to die. Sorry. Okay. Great. So again, Tanya, thank you. So here we continue with our pre-order traversal. What's the next step now? Somebody else. Shania, you on mute?
It's left traversal.
So what are we doing? We're saying left child, right? And we call in pre-order and we pass in visit. And then we say, thank you, Shania. And we say right child, pre-order, and we say visit. Always remember, if there's one thing you have to always remember left comes before right, regardless of what you're doing. Okay, awesome. Cool, so this is pre-order. Let's go ahead and test it. We'll test it right here. Test pre-order traversal print pre-order traversal. We'll say tree node pre-order traversal, and we'll get access to our node, which we captured as we went through it. We captured those values. So we'll go ahead and we'll just print node.value terminator. Terminator never has an autocorrect. So we print it out and we'll just put a print statement here. Okay, so we said the value should be 4, 5, 2, 6, 7, 3, and 1.
Alex.
Yeah.
Do you know if there's a way to run certain lines of code in order?
Certain lines of code in order.
Yes, I'm just asking.
It depends. I mean, if it's a closure, it's not going to run in order of the call.
Oh, okay.
But if you just have like print statements 1, 2, 3, like if I just have print statements procedurally, it's going to get called in order. You could get deeper and create dispatch queues individually.
Yeah, something like that.
Yeah, you could do that. So you could take a look at like dispatch group.
Okay.
So I'll take a look at dispatch group. Dispatch group. And then you could create like queues and stuff.
Okay.
And then you could use, yeah. Cool. Take a look at that.
All right. Thank you.
Very good. Okay, so let's print this out and see what we have. What did we do? We did pre-order, right? What's happening here?
It's correct, Alex.
Yeah, that looks right.
Am I just writing it out wrong?
You just comment like 452. It's wrong. Yeah.
Okay.
It's supposed to be 1, 2, 4.
Oh, we did a post order first?
We did.
That's what I did. I'm sorry.
Post order's next.
We did a post order first. You know what? Let's just do this. Sorry. I'm like,
No, in our notes pre-order like this.
Oh, okay. Okay. Sorry. sorry. Okay. I'm looking at the wrong part of my
You
iPad.
get confused.
Yes, I'm looking at the wrong part of my iPad. I'm like, why is this like this? Okay. Luba, stop me next time. Luba?
Stop, Alex.
What's that? What'd you say?
I said stop.
Yeah, stop me next time. Like, yeah, I'm going ahead of myself. Okay, so pre-order, that's pre-order, and if we run it again, that's what we have. 1, 2, 4, 5, 3, 6, 7. Okay, so that's good. That checks out. Everybody? Awesome. Any questions before we move on to the last one? All right, great. So let's move on to the last one here. Go back to our extension and we'll complete by writing function post order traversal. Again, we have a closure. In TypeScript, this is the full stack, where I have my arrow functions with an equal sign like this. I should just start doing TypeScript, right? I'm a full stack web developer, instructor. So here we have binary tree node, doesn't return anything. Somebody else I haven't heard yet today. Mr. Howard, sir, do we need to give you a mic? Howard, you unmute? Howard?
Hello.
Yes, sir. How you doing?
I am trying to clear my MacBook of crap.
Of crap. Did you clear out the derived data?
Yes.
How much derived data you had?
I'm not sure.
Okay.
Not too much.
You're trying to install Xcode 11.4?
Yeah, and I don't have enough space.
Did you delete Xcode? Well,
no.
You don't want to delete it. I'll probably say delete it after this. That way you free up, what's that, 8 gigs or whatever it is?
I have about 20 gigs now.
11.4?
About 20.
You have 20 now?
No, yeah, 20 gigs available now, but I still
Okay,
have
so
72 gigs in other.
Yeah, I know the other thing is annoying. I would probably delete Xcode though, and then that frees up like 8 gigs, and then you're okay. I think you probably need 24 at the end of the day to install it. Does that make sense?
Yeah.
All right, try that and let me know how it works out. Okay, so what are we doing here in post order traversal, sir?
Well, it's basically the same thing, except visit is on the bottom of right.
Okay, awesome. Thank you for that there. When are we going to see your video?
I don't know. On my computer now, I don't have a camera on it.
You don't have camera on your MacBook?
No, on my desktop.
On your desktop. Okay.
Yeah.
Okay. I see you. When's your birthday? I'll get you a camera, man.
He's lying.
I know you. I know he's twisting the truth. All right. So let's go ahead and do left child. Thank you, Howard. Called post order. Post order, we just pass in visit, and then we do right child. Post order, we pass in visit, and lastly, Howard says just go ahead and visit self last, because this is post order. We visit node last. Cool. So post order traversal, make sure you're calling the right things here. Left child post order, right child post order, and we in post order. Let's go on. Any questions before we move on to the test? Okay, cool. So let's move on to the test part of it. This is for Mr. Benvenido. He could take a look at that. And let's go ahead and test post order traversal. We say print post order traversal. And we call the tree node. Make sure we call in the tree node. That's the first node we have. And we say post order traversal. We have a node argument. You could just print out what that node argument is. Node.value is the value. Again, it could be any type of value. It's a generic. And we use terminator here to override the default terminator. So this overrides the default new line terminator. And what did we say the values are? So we said 4, 5, 2, 6, 7, 3, 1. If we run that, we get 4,